Okay, good evening, everyone, and welcome back. Today is the 10th talk of the Exoplanet course series. And today we have with us Dr. Jacob. I would now request Dr. Ravi to kindly introduce our speaker for the day.
All right, everyone, thank you for coming. So we have today Dr. Jacob Haqq-Misra from Blue Marble Space Institute of Science. I've known Jacob since last 16 years, and he's one of the best well-known researcher in exoplanets and planetary science and habitability. And Jacob is also an accomplished musician. He has a rock band called Mystery Train. If you are interested, there are some videos online. If you can go ahead and look. But Jacob is also very familiar with people who work on policies and space settlements. He wrote several books and has authored numerous publications. And Jacob is a very, very prolific scientist in terms of publishing papers. So Jacob, please go ahead and go ahead and share your slides.
All right. Well, thank you for that introduction, Ravi. And yeah, time has gone by fast. I didn't realize it's been 16 years already since we've been working together, which is amazing. So it's nice to meet all of you. Thank you for inviting me to your class. As Ravi mentioned, I work with Ravi and other astronomers and astrobiologists in trying to understand planetary habitability, and specifically where are the places that we might look for evidence of a planet that might support life, or at least be able to support life. And so what I'll tell you today in this talk, and the kind of work that I do, it's using climate models, the kind of computational tools that we use for understanding climate on Earth, weather predictions on Earth. They all come from the same lineage, but we apply these kinds of computational models to thinking about Earth through its history, Mars through its history, Venus, and then exoplanets. Specifically interested in, as we have more advanced ground-based telescopes, space telescopes like the James Webb Space Telescope, next generation telescopes. We're actually being able to not just identify planets that are close to and at the size of Earth, but then working towards actually being able to look into the atmosphere of those planets and figure out what might be there. So I know you're going to talk about biosignatures later, so I won't get into that, but just to give you context, this is understanding how do we even think about which planets around other stars might be good targets for searching for life. And for that matter, how do we understand how this idea of habitability has changed over Earth's time, and what does that tell us about the solar system planets? So I'll start with a very simple question. Why is Earth habitable? And what we talk about, there's a lot of things habitable could mean. Habitable is, if you look at the word, it's ability to have a habitat or ability to be inhabited. So habitable does not mean inhabited. We don't, there's sort of two questions. Can the planet support life? Does the planet have life? So we're just going to focus on the first one. Can the planet support life? And when we talk about Earth, there are a lot of reasons, but one major reason we're going to focus on, what makes Earth habitable, is the fact that we can have liquid water on the surface of the planet. Earth is unique in this case in the solar system. It's the only planet that has surface oceans. And there's lots of other factors that contribute to habitability, but this is certainly a major one, because if you don't have the accessibility of liquid water, everything else we know about life is probably not going to be possible, at least the way that we understand it. So why does Earth have liquid water on the surface? It's a good question. So I'm not going to have a lot of math in this talk. I understand it's a really broad audience, but this is nothing too scary here. I think it's just worth thinking about what is the basic energy balance of our planetary system. So you can imagine the sun on the left side of this plot here, way off the side of the screen, and the sun has these yellow rays coming in toward the Earth. And so the sun is so far away, you can imagine the sun rays essentially being parallel as they travel from the sun to Earth. And so the solar energy travels through space toward Earth, And so you can imagine it's essentially a disk of radiation that is then moving toward the sphere of the Earth. And so, this is what causes our seasons, the fact that you get indirect solar heating and the equators gets more direct heating year round, and then the poles get a different amount depending on the tilt of the Earth. But just thinking about this in a general kind of annual average sense, you've got pi r squared. R is the radius of Earth. Pi r squared is the area of sunlight traveling to Earth. That whole energy is distributed over the surface area of the Earth, and then the Earth heats up. And so in terms of energy balance, energy in is the sunlight has to balance the energy going out, which is the infrared energy given by the Earth, which is heating up. This is the Stefan-Boltzmann law. So you've got sigma t to the fourth, and you've got a surface area of 4 pi r squared over the Earth. So that's your energy balance: energy in, sunlight; energy out, infrared radiation. So if that's all that was going on, we can write down this energy balance equation. So we've got S naught. S naught is just the amount of sunlight, and we've got that at 1370 watts per meter squared. There's this other term here, 1 minus alpha. Alpha is the albedo. How reflective is the Earth? This has to do with clouds largely. Clouds are very reflective. Surfaces like deserts are very bright. They're also reflective, and even oceans can be reflective at it's a high incident angle. So on average, about 30% of sunlight that comes in is reflected away from the Earth. About 70% is taken in by the Earth system. So we just have the term, the amount of sunlight coming in, 1370 watts per meter squared, times this 1 minus alpha, so we get 70% coming in. And then we just have these geometric terms, pi r squared going in, and then that's equal to this 4 pi r squared times this Stefan-Boltzmann factor, the sigma t to the fourth. Okay, so this is our energy balance. If that's all that's going on, then the Earth's temperature is 255 Kelvin, minus 18 Celsius. So something else is going on. This isn't right because we're standing here. We are not frozen. So what's happening is there's actually a greenhouse layer of atmosphere that keeps us warm. This is an important point that you hear about climate change, global warming in the news. I mean, obviously this is important. It's not just a news issue. This is a scientific issue. But the greenhouse effect is not a bad thing. Too much greenhouse gas, in increasing concentrations due to human activity can cause some problems, of course. But if we did not have the greenhouse effect at all, Earth would be frozen. So the greenhouse effect is good in general because this is what helps keep the planet warm and above freezing and making it habitable. So in this diagram here, you can see now it's a little more complicated. It's not just energy in, energy out, but you have this, S naught, 1 over A. The divided by 4 is just because we've got a slightly different geometry here. Don't worry about that too much. And if you're interested in this, I can point you to where you go if you want to work out problems like these. There's a bunch and they're fun. You get the sunlight coming in, hitting the ground. In this diagram, the atmosphere is this IR absorbing layer. That's usually things like water vapor and carbon dioxide, other greenhouse gases, things like methane, nitrous oxide, but water vapor is the major one on Earth, and then carbon dioxide as well. So in this diagram, the sunlight goes through the atmosphere, heats up the ground. The ground heats up at sigma Ts, the surface temperature, and the ground then sends infrared radiation up into the atmosphere. But instead of going out into space entirely, the infrared radiation gets absorbed by the atmosphere, by this absorbing layer. And then you have this other term on the right, sigma Ta, the atmospheric temperature. You've got a component going upward and downward. So there is still radiation going up into space, but you also have the atmosphere contributing additional warming to the ground. And so when we look at this, there's 2 arrows going down into ground. There's the warming from the sun. There's the warming from the atmosphere. And this is how a planet is able to maintain temperatures higher than sort of that below freezing equilibrium temperature I showed you earlier. Now, this diagram is, even for a simple model, it's not quite complete. what we've added here now, you notice there's this epsilon term on these arrows on the right, and I won't get any more complicated than this. So hopefully you're with me. But just to finish the complete schematic cartoon calculation here, we still have sunlight coming in, going through the atmosphere, but now we have epsilon sigma ts going up, and then there's an arrow that's transmitting through the atmosphere. There's 1 minus epsilon term. So all this epsilon is doing, it's just saying the atmosphere is more complicated than what I've showed you previously. You have some fraction of radiation from the ground that is absorbed by the atmosphere, and some fraction that transmits through it. And if you really want to look at it like we will in more complicated models, well, that has to do with what's the atmosphere made out of. Is it a lot of CO2? Is it a lot of water? Is it a more dry atmosphere? So we've encapsulated all that in the simple model with just this epsilon term. So epsilon, the fraction epsilon is what gets absorbed. The 1 minus epsilon is what gets transmitted through. And then the same is true for the atmospheric component there, that only the epsilon fraction is what actually is going to get absorbed by the atmosphere. So I only show you that so we can do the analogous calculation. If you solve this set you solve the system, you've got an expression for the surface temperature. If you set epsilon to 0.77, this gives you something more realistic like what we have today, the mean annual temperature of Earth, 288 Kelvin, about 15 degrees Celsius. So this is more believable in terms of comparing to what we have on Earth today. So all I was trying to do with these last few slides is use these very simple models. First of all, to show you what is a climate model, even though these are very simple calculations that you can do analytically and it's just algebra. This is the simplest kind of climate model you can have. And then the more complicated climate models that I'll show you results from in the rest of this talk are really just building upon this kind of concept where we're thinking about energy balance, sunlight going in, ground heating up, going out, the atmosphere heating up, and then of course what that atmosphere is made of is really going to impact our calculations. So here's a slightly more realistic version of this energy balance. So I've started with just the sunlight coming in. So you see the star at the top with the number 100. So these are just percentages in terms of the fraction of energy that goes into different sources and sinks. So you have the sunlight going in. There's a big thick arrow going down to the surface. So about 47% is absorbed directly by the surface. But you can see up to the left, 19% is absorbed by the atmosphere and 4% is absorbed by the clouds. And then in terms of what's reflected away, that's that 30% I mentioned again, about 23% reflected by clouds and about 7% reflected by surface. So we have, of the energy going in, 30% goes away back to space because of Earth's albedo, and about 70% gets absorbed. So that's the incoming solar budget. If we then look at what the surface and atmosphere is then doing, you could start at look at the orange. I'd say look at the orange, yellow arrows first on the right. So the surface is heating up. You've got some amount of radiation emitted by the surface, a lot of which is absorbed by the atmosphere, and some of which is emitted directly into space. You've also got these latent heat and sensible heat terms. So Earth has water on it. So as you heat up Earth, you actually get phase changes in water. The water evaporates, and that contributes to your overall energy budget. You've also got just sensible heat, just rising air from having your atmosphere in motion. And then you notice the red arrows. This is the atmosphere itself heating up. The atmosphere has energy. It radiates both up toward the atmosphere and down toward the ground. And then even clouds have a little bit. When the clouds heat up, they emit some radiation. So this is really no different than the simpler models I showed you in earlier slides, but this has some numbers to it. There's a few more processes going on. And so then you can maybe imagine already how you could think about taking some of these processes, representing them mathematically in a computational model, and then you could do more specific calculations about, well, how much radiation is being emitted by clouds versus, phase changes in water vapor and things like that. So yeah, this is how our planet works in terms of energy balance. So moving from energy balance to a climate model, here's just a really general schematic of the kinds of dimensionality you can have to climate models. So on letter A, you have a zero-dimensional climate model. So that's imagining the whole planet like it's a point or a box. That's basically what I showed you on the earlier slides, where we've got these arrows coming in, arrows going out, but that's not really a dimension. All of those arrows are hitting the same point. We're treating Earth's surface as if it's all the same. If you heat one part, you heat it all. So that's what we've been looking at, is a zero-dimensional single point or box model of the climate. And you can learn things from that. It's a great place to start. And a lot of times you can solve those kind of box models analytically with just algebra. Now, a more complex model, and then one that I'll show you, I'll focus on in a bulk of this talk. In letter B, you have a one-dimensional model, specifically height. You would use depth if it was an ocean model, perhaps, but in height, where the bottom of the model is surface, and you're going up to the top of the atmosphere, and you've got sort of a column of these boxes. And we use these boxes because we're just representing the real continuous climate, going from the surface at, the 1,000 millibars up to, the height where the atmosphere is very thin. You have to kind of separate it into discrete boxes in order to do the calculations. And I can get into that more, but since it's not really a climate, computer science talk, I won't dwell too much on that unless there's questions, of course. But in order to essentially solve the differential equations, you have to do this finite differencing, where you create a grid, and then you're calculating the derivatives across the grid points. So you can have a one-dimension column model. You can have a two-dimensional model where you have vertical dimensions and different columns. There's different ways you could think about combining these columns. But once you start thinking about that sort of two-dimensional model, you can then think about moving towards a full three-dimensional model, where you don't just have a column, but you're really representing a sphere, and the grid points don't just communicate in a vertical sense, but there's also horizontal information exchange. And so toward the end of the talk, I'll show some results from 3D models as well. To focus a little bit more on the 1D model, and specifically because I'm going to be using this in the next several slides, it's called a radiative convective equilibrium model. It's one-dimensional again, a column like I just showed you. What the name means is there's radiation, like we've been talking about. You have incoming solar radiation, that's at shorter wavelengths. You have outgoing longer wave infrared radiation coming from the surface. But in addition to that radiation balance, there's also a process of convection or convective adjustment. So the model will also look at sort of the vertical profile of temperature and the vertical profile of water vapor and energy. And if there are instabilities, then the model will make an adjustment to make sure that the model never becomes unstable. You should have a nice smooth decreasing profile of temperature as you move up in the atmosphere through the lower layer of the atmosphere, the troposphere. And then as you get to the stratosphere, the mesosphere, then temperature should be fairly steady at that point. And so if you don't get that, the model has some algorithms in it to make sure that you are getting this sort of nice stable vertical profile rather than an unstable profile, which would represent more energy stored in the climate that should be released as weather or something like that. So this is really looking at a long-term average climate for a planet, where the surface again is just a single point, but we're resolving the whole column of the atmosphere. The layers of the atmosphere can contain different greenhouse gases. The main ones we're going to focus on are water vapor and carbon dioxide. I'll also mention with water vapor, we don't really add extra water vapor into the model as a free parameter. Water vapor is really determined by assuming that the surface is a reservoir, like an ocean, so a reservoir of, not necessarily infinite water, but a very large reservoir of water. And as the planet warms, the Clausius-Clapeyron relationship determines the vapor pressure of water, and so you can very simply calculate what the atmospheric water vapor pressure should be based on the temperature, which just assumes that there's available water in an ocean to evaporate as needed. But carbon dioxide and then any other greenhouse gases that we want to consider, those have to come from somewhere else, and we'll talk specifically about the CO2. So that's kind of the end of just focusing on energy balance. We're going to now apply the energy balance to thinking about this question of habitable zones and understanding planetary habitability. What requirements are shared by all life that we know of on Earth? Well, there's maybe more than these two, but carbon-based organics is one, and liquid water is another. Now, I won't talk too much about the carbon-based organics part, but there's a lot that's written on this, and if you're interested in this, you should certainly investigate. There are some astrobiologists who think about non-carbon-based type life, but carbon is a really great, a great atom. It has 4 binding sites. We see carbon everywhere in the universe, so that's at least one possibility. But liquid water is really important. All life that we know uses liquid water, at least in some point of its life. And most organisms need water at all points of their life. But we've not yet found any kind of life on Earth that does not need liquid water at all. So based on that, I'm not going to say that there cannot exist life that is not using. Of course, there could be something weird in the universe that's silicon-based life that uses alcohol solvents. Sure, we should be imaginative. I can't say that's not going to happen. But based on what we know, life needs liquid water. And so if we want to place constraints on the type of life that we know, while still being broad, we're not saying it has to be DNA, we're not saying anything else about it, but liquid water seems to be something that is used by all life on Earth. So that's at least one constraint that we can use to think about which other planets might be good places to look for life and look for evidence of habitability. When we look at Earth in the context of the solar system, well, Earth has these oceans on it. Venus is really warm. Mars is really cold. Now, possibly both of these other planets had oceans before. It looks like Mars has evidence of having had ancient oceans, probably a northern ocean. And that's one of the goals of the ongoing Mars exploration program, is to really understand to what extent could Mars have had this ancient ocean, and maybe was there opportunities for the origin of life at a time in Mars history. But today, Mars is too cold to hold on to that ocean. And as we'll talk about later, it may not have ever actually been, Mars may not have ever had the potential to really hold on to an ocean for very long. But that's an open question. But Mars is too cold today. Venus may have had an ocean a long time ago, and we'll talk about this a little bit too. But if it had an ocean by today, the ocean has boiled off, and some of it escaped into space. And today it's 800 degrees on the surface of Venus. So we call this the Goldilocks paradox. Goldilocks is the fairy tale where she wanders into the home of the 3 bears, and there's 3 bowls of porridge. One is too hot, one is too cold, one is just right. So the question is, well, why is Earth just right for life, whereas our neighboring planets, which Venus is almost the same size as Earth, Mars is just a little bit smaller, why are those planets not also teeming with life? And Earth somehow seems to be in this sweet spot. So this is what we call the habitable zone. It's what region around a star is where a planet like Earth could maintain liquid water on its surface at some point in time. So right now, today, in this point in history, we would say that Earth is within this habitable zone. because we've got liquid water on our surface today. Venus is not in the habitable zone, can't have liquid water on its surface, and same to Mars. Mars is not. So you can think of it as this band going around a star, and that band tells you where it's not too hot, not too cold, but it's just right for habitable conditions. And we can also talk about the continuously habitable zone. So this is just acknowledging that stars get brighter with time. Over the course of their adult main sequence lifetime, a star gets a little bit brighter. And so if you're in the habitable zone at one particular instance in time, well, 2 billion years later, the star has brightened. And so that habitable zone may be pushed out a little bit. And so the planet may have moved from being in the habitable zone to being past the boundaries of the habitable zone. Well, we'll talk about this later too, but just to start by defining the terms. This is what we're really interested in, is how do you use these kind of energy balance, radiative convective equilibrium models to calculate the boundaries of the habitable zone. There's an inner boundary, how warm can a planet get before it's unable to be habitable, and then what the outer boundary is, how cold can a planet get before it's no longer habitable. Now, these definitions, and you see this, the citation, Michael Hart, Icarus, 1978. This was one of the first papers to really attempt to do a calculation, a quantitative calculation of the habitable zone using the kind of zero-dimensional energy balance models I showed you earlier. And so in Michael Hart's calculation, it says, well, if you look for this continuously habitable zone, because that's what you need. If you want a planet like Earth to have developed life, which what seems to have happened is that life has been on Earth for almost its entire history. It's 4.5 billion year history. Seems like almost all that history, Earth has had liquid water and life. So if that is the case, then you have a very narrow, continuously habitable zone around the sun, according to Michael Hart's calculations. So, 0.95 AU. So if Earth was moved in just, 5% or so closer toward the sun, it would be too hot. You would start to boil away the oceans. You would get this runaway greenhouse. Earth would be like Venus, according to Michael Hart here. And then if you move Earth just 1% away from the sun toward Mars, just 1%, you get runaway glaciation. The ice sheets grow, the Earth turns into a snowball. And Michael Hart says that it's even worse news if you go to other spectral types. If you go to a K dwarf or an M dwarf star, dimmer than the sun, that you have an even narrower continuously habitable zone. So Michael Hart concluded from this, is like, look, it looks like there's a very narrow range where Earth can exist around the sun and be habitable. So maybe Earth is the only habitable place in our galaxy, and we just got really, really lucky. So whether or not you agree with this, this was the first calculation, and it certainly motivated others to look at this problem and say, okay, if we take the Earth as it is today, with just those processes that Michael Hart included, this is the answer you get. But the question you can ask is, are there any other processes that operate on longer timescales, on these 100 million to billion year timescales, that may change the way that a planet behaves at different points in its orbit around a star? As I mentioned, so the inner edge of the habitable zone determined by loss of water from the runaway or moist greenhouse effect. So Venus is one example where we have these thick clouds on Venus. There may have been an ocean at one point on Venus, but today it's a very hot world. And so these are calculations that Jim Casting did. Ravi and I both worked in Jim Casting's group at Penn State. And so, Jim was very motivated by Michael Hart's calculations, and he was, trying to look at both the inner and the outer edge to see how much do you really want to believe Michael Hart's calculations. And so in this, there's a couple of things going on here, but on the x-axis, you have the solar constant relative to present Earth, and you can see where it's 1, that's present Earth, and then we have the surface temperature on the y-axis. So just first to start, look at the solid line with TS marked in red. You can see that as the solar constant goes up, so you're brightening the sun. You can either think of it as either brightening the sun, or you can think of it as actually moving the planet closer to the sun. It doesn't really matter. It's conceptually how you want to think about it. But it's if the planet is at a closer orbit to the sun, it gets more solar energy. And so as that happens, you get warming. But right around this 1.4 solar constant, you see you get very, very rapid warming, which is marked as a runaway greenhouse. That is corresponding to a point of rapid hydrogen loss. So if you look at the dashed line, you can see that as the planet warms, stratospheric water vapor slowly decreases, and then there's a very, very rapid period of hydrogen loss. Once the hydrogen is all gone, you're essentially evaporating the oceans. And what you're saturating the whole stratosphere with the whole troposphere, the lower layer of the atmosphere, the whole troposphere is saturated with water vapor. Once it's saturated, then some of the water vapor starts to make it out into the stratosphere. The stratospheric water vapor gets hit by photons, and the hydrogen escapes into space. And so when this happens long enough, eventually you lose all of your ocean as water vapor into the atmosphere, and then it all escapes as hydrogen into space. Once that has happened, then you get this really rapid temperature increase because you've got a very high greenhouse effect, and you've lost a lot of your water vapor. And so then the planet reaches very, very hot temperatures, and that's kind of the situation that we see with Venus today. I know these calculations were redone with a improved model that Ravi Kopparapu led. The axes are inverted in this one, so just think about it backwards from what we looked at the other one. So here we have surface temperature on the x-axis, so cold on the left, warm on the right, and then we have the effective, the amount of sunlight scaled to the sun on the y-axis. So in this case, you can see as the planet warms up, you hit a point where you get this moist greenhouse regime. So the moist greenhouse is what I was describing when the troposphere is saturated in water vapor, the stratosphere is starting to get wet, and you're starting to get this hydrogen loss from high energy photons. So if you see a planet like that in this moist greenhouse phase might be able to last a while. It really depends on how much ocean you have. But if we were to see a planet like that, you would know that it's not in a long-term steady state, that eventually it's going to lose all the oceans. But that takes a while, and you can see the moist greenhouse phase lasts up until the planet gets really hot. And at that point, you get a runaway greenhouse where then the temperatures increase much more rapidly. So the implications for this is that the inner edge is at about 0.97 AU. So actually, in this sense, this is not that different than what Michael Hart was suggesting. He's saying that if we take these water loss limits, then Earth is relatively close to that point. Now, you could ask yourself, how close are we? Well, I don't think we're close enough that anthropogenic climate change is going to push us into a runaway greenhouse. I believe this has been looked at, and I think the answer is no, probably not. But the question is, how many, do we have 1 billion years, half a billion years before the sun brightens enough that you have the moist greenhouse start to set in? And then that's an important question for the future of Earth. So there's also the fact that clouds and other negative feedback could push this inner edge to closer to the sun than we are now. And I'll even show you an example of where we found that this is the case for other types of planets. But without clouds, with just doing the energy balance with the radiative convective equilibrium model, Earth is pretty close to the inner edge of the habitable zone. So the inner edge is determined by the loss of water, by the runaway or moist greenhouse effect. Now, the outer edge, how far can you move the planet away from the sun and still maintain habitable conditions? Well, that depends on how large the greenhouse effect might be. So we'll take this conservative approach in this talk and these calculations. We assume that there's just carbon dioxide, which I'll talk about the source, and water vapor, which is from assuming an ocean. Now, of course, you can have other greenhouse gases. We do have them on Earth, and they could be important. So you could think about things like methane, ammonia, ethane. The reason I'm not considering them right now is you have to think about what is the source of those gases. Doesn't mean they're not there. They may be on exoplanets, but many of these greenhouse gases might be created by biology. That may be biology unique to Earth, or it may be processes that we just don't understand fully how they would operate on exoplanets. And then some of them have very short lifetimes. So ammonia, for example, is really difficult to get in large abundances because it gets destroyed very quickly. But as we think about habitability in general, of course, we should be thinking about other types of gases that could be in atmosphere. Hydrogen is one that there's a lot of papers that look at how adding hydrogen into an atmosphere can extend its habitability. So saying all that, we'll just focus on CO2 and water vapor, but know that other greenhouse gases can also have an impact on this. The main process that I want to talk through about what regulates carbon dioxide on a planet's atmosphere is the carbonate-silicate cycle. So this is the long-term carbon cycle on Earth. There are shorter-term carbon cycles that you might hear about, and those are more relevant to present-day climate change. The carbonate-silicate cycle operates on a timescale of about 500,000 years. So this will not have much effect on anthropogenic climate change. But what this does is this is the process that helps regulate the amount of carbon dioxide in a planet's atmosphere on these much longer timescales. So the way this works, I'll just talk through it. The punchline's at the bottom. Atmospheric CO2 builds up as the climate cools. Well, why is that? I'll explain a little bit. It starts with volcanoes. You have a reservoir of CO2 in the interior of the Earth. A volcano erupts. There's CO2 and other gases that come out of volcanoes, but the volcano puts CO2 into the atmosphere. During rainfall, rain will dissolve some CO2 into it and into carbonic acid, and the rainwater will hit the ground, and you get this weathering process. So that's this chemical reaction on the left underneath the land. You have calcium silicates plus carbon dioxide plus water. So that's the dissolved CO2 in rainwater, carbonic acid. That weathers these silicate rocks, and you get these calcium ions and these bicarbonate ions and a silica dioxide. So you imagine you have weathering of rocks that is then causing ions to run into rivers and eventually make their way into the oceans. And so you have these calcium and bicarbonate ions in the ocean. What happens in the ocean is on Earth, where there's life, organisms actually use those things to make shells. And if you don't have life, though, you actually just saturate the oceans with those ions until they start to precipitate out. And so either way, you get these calcium carbonates that then precipitate to the seafloor, as well as some CO2 and water. Those calcium carbonates then get subducted into the Earth's interior. There is this is a fun typo, metamorphism, because metamorphosis is a caterpillar turning into a butterfly. But the rocks have a metamorphism where you go from calcium carbonates and silicon oxide to calcium silicate oxide and CO2. So that releases the CO2, which can go back into the volcano. So there's the cycle of the story of how the CO2 goes from volcanoes to weathering to oceans to subduction and back to volcanoes. The weathering step, the rate of weathering, when the rainwater hits the rocks and breaks it apart into these ions, that is a temperature-dependent effect. And so as the climate cools down, the weathering slows down. And so as the weathering slows down, you get fewer ions reaching the ocean, and it slows down the whole process. If it gets really cold, you almost stop weathering to a point, and you build up more CO2 in the atmosphere from these volcanoes. Conversely, if you warm the planet, the weathering increases and you draw down even more CO2. So this is sort of a thermostat, a regulator on Earth's climate. If you gets too cold, CO2 builds up and you get more greenhouse effect, and that helps the cold from being runaway. If it gets too warm, well, it draws down CO2, and then that helps you from getting sort of into a runaway warming effect, at least to a point. So this is how a planet like Earth, with active plate tectonics, recycles CO2 and regulates its climate over long periods of time. So this carbonate silicate cycle defines this habitable zone. And I mentioned this briefly before, but it's important to emphasize again. We're specifically talking about rocky planet with above freezing temperatures. The atmosphere has nitrogen, water vapor, CO2, and you have to have a mechanism for recycling volatiles, like plate tectonics. Maybe there's another way other than plate tectonics, but this is not for a Jupiter-like planet or anything like that. This is sort of what we mean by Earth-like. It doesn't have to be exactly like Earth, but it has to be rocky with this nitrogen-based atmosphere and something like plate tectonics. You also have, so what is really controlling this outer edge? Okay, so if the planet gets colder, CO2 builds up. Well, what are the limits to that? How much CO2 can you build up in a planet before you reach this outer edge? Well, there's two factors, and one of them is really what causes this limit. But as you move away, CO2 begins to condense. Just like we have water vapor condensation, you get in closer to the triple point of CO2, and you form CO2 clouds. You might form CO2 ice on the surface. We see this on Mars. In some of Jim Casting's early models, he assumed that CO2 condensation was the outer edge of the habitable zone, that once CO2 began to condense, that was the limit. That may not necessarily be the case, and it's worth understanding the extent to which CO2 clouds can contribute to the planetary energy balance. So it may or may not hurt habitability. It may not necessarily be the end state of a planet's habitability just because you have some CO2 condensation. What's a more hard limit is the maximum greenhouse effect that you see in a planet's atmosphere. As you increase CO2, you get warming from this greenhouse effect up to a point. Once it gets thick enough, you actually get Rayleigh scattering that then scatters away incoming sunlight to the point that it counteracts the warming, and you no longer get additional warming from adding additional greenhouse gases. So that this puts the outer edge at about 1.7 AU. And so here's a calculation, again, that Ravi performed, where these calculations were done by actually taking the climate model. You fix the temperature to the freezing point of water to 273, so Kelvin. So you know that the planet is just at the point where it has liquid water on the surface. And then for different values, different amounts of carbon dioxide in the atmosphere, you calculate, well, what's the balance between the sunlight coming in that allows you to get these at freezing, at melting point temperatures. And so you can see at a one bar 10 to the 0, one bar partial pressure of CO2 and up, you get an increasing trend all the way up to about 7 or so bars of CO2 pressure. Then you get this maximum greenhouse effect. So you can add a lot of CO2. Earth, if I'm using units that you may not be familiar with, so sorry about that. So Earth today, we're around 400-ish parts per million of CO2. The pre-industrial value is about 280 parts per million. The total pressure of Earth's atmosphere is 1 bar, 1,000 millibars, right? So 1 bar. So already here we're talking about, well, what if our Earth pressure was doubled and you had another bar of CO2? That's what I mean by 1 bar of CO2 pressure. So at the maximum greenhouse effect of 7 bars, that would be like Earth's atmosphere is 7 times as thick, and it's all the additional thickness is carbon dioxide. So that's a very different atmosphere already. But the point is that beyond that 7 bars, more CO2 doesn't warm your planet anymore. More CO2 actually cools the planet. And that's, again, this Rayleigh scattering. The atmosphere is so thick at the upper layers of the atmosphere that sunlight is being reflected away in greater quantities, is being scattered away, rather than being absorbed to actually heat up the planet. So this is what limits the outer edge of the habitable zone. Now, as I mentioned, CO2 condensation leads to cloud formation. So clouds, again, may push the outer edge further away. And this is something that we can't use these one-dimensional models for. When you see a picture of Earth, you notice that Earth has fractional cloud cover. About half of Earth is covered in clouds at any given time, at a given point in time. So that makes these calculations really complicated. If sunlight comes into the Earth and it hits a region that is cloudy, that's a different energy balance than when the sunlight comes in on a cloud-free region. When you have both of those things going on in the planet all at once, and the clouds are forming dynamically and changing with the time of day and changing with the season, you can't really use this one-dimensional model where you're averaging out everything as a point. You have to use a 3D model that can actually represent fractional cloud cover in some way, and that can actually handle these dense CO2 atmospheres. And this is an ongoing problem on how to do this, how to do clouds well for Earth. Water vapor clouds have huge uncertainty. That's probably one of the biggest uncertainties in present day Earth climate change. So for exoplanets, we're actually wanting to go one step further and have carbon dioxide clouds in the model. So there are models that try to do this, but it's very difficult, and it's not always clear that even if you get an answer that, how robust that answer is. So this is part of where the field is at in developing 3D models that can handle these more exotic atmospheres. And just to show you, we know that Mars has CO2 clouds. Here's some images from Mars Express, showing just clouds at different wavelengths. And we have CO2 ice caps on Mars. So Mars sits toward the outer edge of the habitable zone. It's not habitable right now, but it's kind of on that edge where you can see what are the effects on a planet where there is a lot of CO2 and you're past that outer edge. You get this CO2 condensation effect. So if we talk about the continuously habitable zone, so not just where the boundaries for the habitable zone right now, but how has this zone changed over time? Now, again, we know that since Earth has been habitable for its whole history, Earth has to have been in this continuously habitable zone from 4.6 billion years ago up until today. So the inner edge stays at the same, about 0.95, 0.97, because the sun is just as bright now as it's ever been, and so Earth is kind of teetering close to that inner edge now. Further in the past, that inner edge was closer to the sun. But if we're talking about the continuously habitable zone, it's basically where we have it now. The outer edge, well, when the sun was 30% less bright, you couldn't be quite as far out in orbit if you wanted to be warm. So, if we assume that outer edge was at 1.8 AU, then the continuously habitable zone edge is at about 1.5 AU. So that's an even narrower range where a planet like Earth around the sun can maintain its habitability for a 4.6 billion year time period. By contrast, Venus would have been within the instantaneous habitable zone at the formation of the solar system, but that inner edge moves outward, and eventually Venus got too hot and was no longer within this continuously habitable zone. At the same time, Mars was not in the habitable zone early on. Today, Mars might actually be within this habitable zone, but Mars is too cold, it's too small, it doesn't have an active carbonate silicate cycle. So, in theory, you could even think about if Mars was like Earth and it was larger and it had active plate tectonics, maybe today Mars would be more habitable. But 4 billion years ago, Mars would have been beyond the boundaries of this habitable zone. So again, Earth is in this peculiar place where things seem to have been just right for life not to just arise, but to survive for a multi-billion year history. So we can take this and we can also calculate habitable zones and the continuously habitable zone for other types of stars, not just Sun. Hopefully it's mostly astronomers in this class, so I don't have to spend a lot of time on here. Just to remind you though, there are different types of stars. This is the HR diagram. So on the left, on the x-axis, you have O stars that are very, very hot, and on the right you have M stars. The ones that we really focus on, the Sun is a G star, of course. F, G, K, and M tend to be the ones we focus on. The O, B, and A stars are very big. They also have much shorter lifetimes. So we tend to focus on the other stars that are a little more long-lived, and where we've also found planets around. I think that's probably all I need to say here, other than there's a main sequence lifetime of stars, that's their adult lifetime, and then after that the stars evolve into supergiants and then maybe supernova or white dwarf. So we have different types of stars. This is the plot from Jim Casting's Habitable Zone paper from 1993. On the x-axis, we have the distance that the planet is from its star. On the y-axis, we have the mass of the star, and this is just normalized to the mass of the Sun. And you can see there's black dots here representing the planets of the solar system, and an orange band labeled habitable zone. And these are just based on the types of calculations I was showing you before. This is a summary figure. And so if we look at where the solar system is, we're right where the G star mass is. You've got Mercury, Venus on the inside of the habitable zone, Earth within the middle, but you can see it's closer to the inner edge than to the outer edge. You've got Mars on the outer edge, or depending on how you do this calculation, Mars might be closer to within the habitable zone today, and then the outer planets are further beyond. What is also important to notice is this habitable zone has a slope. And so if we go to K dwarfs or M dwarfs, then the habitable zone moves closer in. Well, this makes sense. These are dimmer stars. They have more energy in the infrared than in the ultraviolet and visible. And so the planets, if a planet wants to maintain similar temperatures to Earth, habitable temperatures, then the orbital distance has to be closer in toward the star. And likewise for F and A stars, the habitable zone is further out. There's also this dashed line, the tidal lock radius. So any planet that's within, on the left side of that tidal lock radius, it'll either be in a spin orbit resonance like Mercury, or it'll be in synchronous rotation like the moon around Earth, where one side always faces the star. And so we don't get that for the solar system, but you notice for M dwarf stars here, the habitable zone is past this tidal locking radius. And at a little bit of time at the end, I'll mention some of those calculations. Here's a much nicer plot that was made with the updated calculations done by Ravi Koparapu. And you can see basically the same punchline. The units are just a little different. So we still have the star on the y-axis here. Now we're showing the effective temperature of the star. On the x-axis, we have the starlight on the planet relative to sunlight on Earth. And so you can see Earth is up here in what's marked the conservative habitable zone. And here we have Mars also within the conservative habitable zone today. And then we've got other exoplanets. You can see that there's a handful that we think about, not that these are planets that have life, But of the planets we've found so far, these are the ones that at least fall within this traditional habitable zone. We may rule out most or all of these planets as actually being good candidates for habitability, but at least it shows that this approach can help us to characterize, what some of the more promising planets might be. I won't talk much about it in detail, but there's a more optimistic habitable zone that Ravi's included on here. And this is really just noting that this inner edge has a lot of uncertainty. There could be clouds or other factors that extend that inner edge of the habitable zone. So maybe it's not actually that Earth is teetering on the boundary of a runaway greenhouse. Maybe, in fact, Venus is closer to that boundary, Venus today, and there's other processes that would sustain habitability on Earth, even if the sun brightened a little bit. So you can read Ravi's paper if you're interested in learning more about that. So I mentioned this very briefly. If you're larger than F stars, you have a much shorter main sequence lifetime, and you might have high levels of UV radiation. This is just an assumption. I'm not going to say there cannot be light habitable planets around an A-dwarf star. So these are just some of the reasons why we're focusing on F, G, K, M, but I really can't say much more about it being impossible. But there are reasons that we think that those larger stars may be less hospitable to the kind of life we know. Here's this is very similar to the other plot I showed, but just emphasizing the tidal locking radius and the time scale. Within 4.5 billion years, if you're around an M dwarf star, then you're orbiting very close to the star if you want to be in the habitable zones, blue region, and you're well past this tidal locking radius. And so to steady okay, we've got enough time to finish some of this. So to study these types of planets, the ones that have this tidal locking geometry, we really have to go to 3D models. So what I've been showing you up till now to calculate the habitable zone boundaries are these one-dimensional radiative convective equilibrium planet models. But because of the 3D geometry of these planets around M dwarfs, where one side faces the sun, one side is permanently away from the sun, you have to think about how the atmosphere transports energy around the planet, and you really can't just make the assumption that the planet is a single point with just a column of atmosphere above it. And so here's a schematic of how you think about a 3D model. So you've got the column of boxes, but then the boxes can also exchange information horizontally. And then you've also got other processes. There's clouds here, there's rain, you could have terrain. So there's a lot of other kinds of physical processes you can represent in a 3D model that are more difficult to represent in a 1D model. Just as a schematic for what we're talking about with this type of planet in particular, so you have a red dwarf star on the right. The planet is in synchronous rotation. So you have the day side of the planet, it's permanent day side. The sunlight is continuously shining on just that day side part of the planet, the substellar point. So the point of the planet is always directly underneath the sun. It's always noon. On the other side of the planet, it's in permanent night, permanent darkness. It is usually cold and icy. Between the warm and the cold side, you have the terminator. This is a region in perpetual twilight. And that might be the most habitable region of the planet. It really depends on the configuration. And then you've got energy transport from the warm side to the cold side. And that, the fact that you have these two hemispheres, there's geometry on the planet that you can't represent in a one-dimensional model. And then there's also this energy transport from one hemisphere to another. And you can't do that in a model that doesn't resolve the surface at all. So this is why we have to go to 3D models. I won't go through the rest of these plots in detail. And I put them here just in case we had too much time to fill, but I want to make sure we have time for questions. So I will just, I'll go through a couple of these. These are some calculations that Jun Yang performed in 2013, really just showing that if you have these planets in synchronous rotation, they can remain stable, and the inner edge can be a lot broader because you get clouds forming on the substellar point, and the cloud provides almost a shielding effect where the high albedo reflects sunlight away and the planet can get closer to the star. And so you can see the red, yellow, and green curves show a planet that has very, very rapid warming. But when you use the 3D model and include these cloud effects, the black and blue lines show you that the rate of warming is much lower, and so the planet can be habitable for a lot longer. So that's an effect. The extent to which you get that effect depends on a lot of the geometry and the physical parameters of the planet. I just show here's just to show, like, these models are 3D, so we're not just getting one temperature, but you get a temperature distribution in color here. You can see on the left, there's warm spots in yellow, cold on the night side. There's arrows showing wind. So all this is showing is the top two panels show the surface on the right and the upper atmosphere on the left. And the top row is a planet with a 9-day rotation period. The bottom is the same planet with a 60-day rotation period. And you can see the wind pattern is totally different based on a 9-day or 60-day rotation period. And so this is where it gets tricky, and we can get into this if you want to talk about it more. But there are a lot of free parameters to some of these planets, and getting better observations will help constrain things, like the greenhouse gas abundances, but then also understanding the planet's geometry and where it is in orbit, and using Kepler's laws to figure out what the rotation period should be. That'll help to constrain some of these models also. Here's one calculation that Ravi and Eric Wolf led, where we looked at these low mass stars. We've got the relative stellar flux on the x-axis. The top panel shows surface temperature. The bottom panel shows stratospheric water vapor. And so you can see for each of these different temperature stars, or planets around the different stars, you see warming, and then a point where there's this dotted line where you hit either a runaway greenhouse or a moist greenhouse. And the threshold at which you reach that is slightly different for each of these different types of stars. And in fact, for the coolest stars, the 2600 and 3000 K, you don't even go to a moist greenhouse phase. You really go from habitability straight into a runaway greenhouse. And this just shows we can use those kind of calculations to calculate the habitable zone. On the top plot, we see a runaway greenhouse and a water loss. The bottom plot, I'm only showing you this because there's still uncertainty. We have the one labeled this steady from this particular paper that the plot was taken from. You see that extends the inner edge from Ravi's 2013 calculations, but then there were other papers published that had slightly different bounds to the inner edge. So this is an ongoing problem. There's even other papers that I didn't show that are published more recently. This is an ongoing problem in terms of how well are our models capturing the behaviors of these planets. These are really different than Earth, these synchronously rotating planets. So there are efforts at comparing different 3D models for these kinds of systems to really try to understand this, because this will be important as James Webb Space Telescope and others continue. Well, the TESS mission, for example, discovers new planets around these low mass stars. These models are going to be helpful for making predictions about what these climates might be like and prioritizing targets for characterizations. And so we want to make sure that the models agree, or if they don't agree, that we understand the spread of model results and understand why they disagree and where we need to put more effort into improving these models. So that is what I have. These habitable zones, especially around FGK stars, are relatively wide. We can talk about whether or not larger stars are poor candidates for habitable planets. They do have shorter main sequence lifetimes. An F dwarf is about 2 billion years. And Earth 4.6 billion years. How an A dwarf may not have enough time, but it's worth talking about. M dwarfs have good continuously habitable zones. Their planets might be in synchronous rotation. Is this a problem for life? It was assumed, in the 60s and 70s that would make the planet uninhabitable. But we've since found with our models and even observing some of these planets that they do have atmospheres, and that atmospheric dynamics is usually sufficient to prevent the planets from, it was worried that they would freeze out their atmosphere on the night side because it was so cold. That seems to not be the case. So we're going to be looking at these M-dwarf planets, and we're going to be characterizing them, mainly because they are going to be the easiest to see and to characterize with the current and near-term future missions. So that doesn't mean they will have life, because we can search for them, but it's where we can search. And so it's worth at least thinking about what would we look for signs of habitability. And then clouds and other dynamical processes may extend the outer edge. It may even extend the inner edge to some extent. And these are difficult problems of 3D modeling that are being worked on. And if you're interested, of course, in getting involved in climate modeling, maybe you do climate modeling, you may know already, but yeah, clouds and other physical processes are an important part for Earth climate change, as well as exoplanet climate. And those may capture a lot of processes that we don't understand at this point. So that is all I have. Thank you very much for your attention, and I'm happy to have a discussion and question.
So we have a few questions. People can unmute themselves and ask. Sorry, Ravi, you were saying something.
Oh, I was just saying the same thing you were saying, and there you can start from the list of questions in the chat, starting from the beginning. Jacob, if you want. So.
Oh, okay, there I see it now. Yes. Let's see. Okay, we have. What about viruses? These do not need water. I'd say viruses do need water because a virus has to infiltrate a cell in order to survive. And so at least in some point of its life cycle, a virus has to be exposed to some water, or the virus dies out. But these are great questions. Yes, absolutely. And this is part of what makes astrobiology fun, is because you get these weird cases. There's spores that don't necessarily need water, but it's in the spore phase of their life stage. But at other phases of their life, they do need water also. What conditions are required for an exoplanet to sustain life? I mean, big question. In general, in this talk, I talked about surface liquid water. Is that a strict requirement? Maybe not. One thing I didn't talk about in this talk, but I guess it's important to mention, the definition of the habitable zone that I presented in this talk, it is not saying that there cannot exist life outside of this habitable zone. I'm not at all making that claim. The habitable zone is useful because it provides a place that astronomers can search. It's a zone where the presence of liquid water is constrained by this carbonate silicate cycle, and it gives you an orbital range where you can predict where would I look for a planet that, if it had a carbonate silicate cycle, then you would expect liquid water to be there. So it's a way to ask yourself, where can we look astronomically for planets that are likely to have surface liquid water? But people talk about oceans on Europa in the solar system. Europa is beyond the bounds of the habitable zone. That's subsurface water. It's underneath ice. Does that mean there is no life? I don't know. Maybe there's life on Europa. So we're not saying that if you're outside of the habitable zone, there's no way for there to be life. But if you're outside of the habitable zone, something else has to be going on. The water's underground, covered in ice, or something like that, or there's other processes that are causing the heating that are not, the sunlight. So the habitable zone is useful for astronomers to help decide where they can look for planets with surface liquid water. Does a meteor impact have any significant role in affecting the atmosphere? Yes, meteor impacts can. There's a lot of papers published on how do planets get their water initially during formation, and so delivery of water from impactors is certainly one possibility for how planets get their water early on. And that there's other there could be other times in a planet's history when meteor impacts might also affect climate. If there's a period of heavy bombardment in an exoplanetary system, in their history. That the heavy bombardment may be reflected in geologic record. That may be a driver of climate change on shorter time scales. So yeah, absolutely. And then the inner and outer edge bound to change, or are they fixed? They definitely change, and that's where the difference between the habitable zone and the continuous habitable zone comes into play. The continuous habitable zone changes, and that expands outward because a star brightens with time over its main sequence lifetime. So what's going on there, the astronomy in very brief, is the stars changing hydrogen into helium. As the hydrogen builds up into helium, energy is released, and the core gets a little denser, and the core starts to contract. As the core contracts, you increase the rate at which the fusion, you increase temperature, and then you increase the rate at which the fusion reactions occur. And so that causes the sun to brighten a little bit. So, 3 billion years ago, the sun was less bright than it was today. And so Earth may have had a stronger greenhouse gas at that time to compensate for it. And so, yeah, so the habitable zone changes as the sun brightens. What particular kinds of observations are needed in order to make our latest atmospheric models more reliable and constrain it to fit larger varieties of planets? Great question. Yeah. So there are a couple things we can do. One is laboratory experiments. So a lot of these models you're calculating radiative transfer in a gas. Essentially, the atmosphere is a gas at a fixed temperature, whatever temperature it's at. And if we're looking at a planet like Earth, well, we understand Earth very well. Earth is very well studied. We understand how a gas like carbon dioxide behaves at Earth-like temperatures. But what if you want to understand how radiative transfer works in Venus? Well, that's a trickier problem because we don't have Venus-like temperatures on Earth. So you have to go to a lab. You go to a chemist who has the right kind of experimental setup where they can have a chamber with a simulated atmosphere with lots of CO2 and heat it up to Venus conditions. And then you can do some measurements to ask yourself how does this kind of gas radiate energy under different conditions. And then you can take that data and put that in your model. And you can do the same thing at cold conditions. What about on Mars or another planet where it's very, very cold compared to Earth? So there is room for actually doing experiments on Earth in labs to help improve these models. Probably any kind of observations we can do on other solar system planets are going to be higher resolution than exoplanets, of course. So if we want to understand CO2 clouds, which might be important for exoplanet climate, Mars is probably the best place to look. And as I mentioned, even representing clouds and models on Earth, for Earth is very, very difficult. Representing carbon dioxide clouds on Mars is also difficult, but it's a problem that people who model Mars climate are studying. And so the better we can understand how carbon dioxide clouds work on Mars, the better that we'll be able to understand carbon dioxide clouds in general in our models for exoplanets. And then the last thing I'll say is just the more we can actually get spectra of exoplanets, then we'll actually have data on what these other planets, what their atmospheres are made of. And that's really what we want, because otherwise we're really kind of either guessing or doing a parameter exploration without a lot of data constraint. Let's see. Could you please explain effective temperature versus relative stellar flux graph again? I can pull this up again. Okay, so stellar, stellar. Okay, I'm not sure which plot they want.
Varun, are you asking
the second last plot?
Oh, the second to last plot.
The one before the conclusions. Yes.
This one?
Yes.
Oh, okay, sure. So let's just look at the top panel to start with. And we'll look at the 4500K system. So this is a planet around an M dwarf, but it's one of the warmer M dwarf. And so if we start at the bottom right of the purple curve, the relative stellar flux is just how much energy is the planet receiving, and it's relative just to the sun. So it's 1.3, so 30% more than Earth gets from the sun. And so as we move up the curve, we're increasing the amount of sunlight that the planet gets. So in terms of what we're modeling is we're modeling planets at different orbital distances. So at 1.3, the planet is at one distance from the star. We move the planet a little bit closer to the star, and we keep doing that. That's what each of the dots are on the curve. When you get to about 1.7, that's the last point at which the planet is stable. So the planet warms up as it moves closer to the star. That 1.7, that you have the 305 Kelvin temperature. And then if you move the planet any closer to the star than that, then you end up in a runaway greenhouse state. And what that means from a climate modeling sense is that you see the energy balance just goes way out of balance, and then the model crashes and you don't get an answer. If you look at the bottom plot, then that's showing stratospheric water vapor. So you have the same line starting at 1.3. You've got relatively low amounts of water vapor in the stratosphere, but the last two dots here you see are above the moist greenhouse line. So what that means, these are stable in terms of the model reaching an answer. The computational model gets an answer, but the water vapor is at this 10 to the -2 moles per mole value. That's the value where we notice that the stratosphere is now moist, and you would expect to start losing water. This model does not actually have a mechanism for hydrogen loss due to photochemistry. So we just take note of the fact that the stratosphere is wet, and in such a situation, you would expect the water to very slowly be lost to space. It might take a billion years or so, but it would eventually be lost to space. And then where the dotted line occurs, that's where you actually get the runaway greenhouse, where then you lose the oceans. Does that help?
Yes, sir. Could you also explain the next plot also?
Sure.
Yes, this one.
Yeah, no problem. So I'll start on the top. The top is the most important. This is the same relative stellar flux. So just the amount of sunlight or how close is the planet to the star. And then the y-axis here, this is the effective temperature of the star. So this is like I showed you in the other habitable zone planets, 4,500. These are all M dwarfs, but that's a warmer M dwarf. 2,500, that's a cooler M dwarf. And so this is showing that, the red line is showing, well, where's the boundary of this habitable zone when the boundary is defined by the runaway greenhouse effect? Where do you get it? And so that's the red line. You hit a runaway greenhouse effect for 4,500K at about the 1.7. For the 2,500, the smaller M dwarf, it's at a relative flux of about 0.9, 10% less than what Sun gets. The green line then just shows, instead of the runaway greenhouse, where do you expect to start getting that stratospheric water loss? And so that starts a little sooner than where the runaway greenhouse occurs. But then for the lowest mass M dwarfs, for the 3,000 and below effective temperature stars, there is no water loss. You just go straight into the runaway greenhouse. The bottom plot, all that's showing is other studies have done similar calculations, and you get different boundaries on this. I think what I'm showing is this study. There's reasons why I think what we're showing here on the top panel is probably more accurate than the other curves in the bottom plot. But I show this for two reasons. One, to show that the amount of improvement we made with these new calculations is pretty significant compared to what was previously published. But even more importantly, the fact that you have this much disagreement shows that this is not a closed question. So what I've shown in the top plot is an improvement, but there's a lot more work to be done by using multiple, different models that are from different lineages to see like how well do we all agree on these boundaries, specifically for these planets around M dwarf stars.
Okay, sir. Thank you. Understood.
Okay, great. Thank you. I'll stop the share. Is there a limit for the number of planets in the habitable zone? How many planets can form naturally in a habitable zone? That's a great question. Jim Casting, our former advisor, he used to like to point out in the solar system, there is sort of an empirical relationship called the Titius-Bode law that just shows there's a geometric spacing to the planets. There's really no physical reason for that. So that's why I didn't even talk about it in this talk. It may just sort of be an artifact of how the solar system is, but not a prediction for other systems. So there's not really a direct way to predict based on the solar system. There's some evidence that lower mass stars might be more tightly packed, and that you might get planets that are more closely in to each other compared to the solar system. The TRAPPIST-1 system, for example, has one planet that seems to be cleanly within the habitable zone, but maybe up to 3 planets that could be, depending on how you what those planets' atmospheres might be. I don't think there's a hard limit for the number of planets. What are the implications of the presence of phosphine on Venus? Right. I think we should search for it. So the phosphine on Venus is a big question, and too much to get into now. But as far as the habitable zone goes, there's not enough phosphine on Venus, and I don't think anybody's arguing that phosphine would be a major atmospheric constituent that would actually contribute greenhouse warming and change the bounds of the habitable zone. So the phosphine on Venus, if it's even there, is more of a biosignature, an indication of biology. And I believe you're talking about biosignatures later in this course. So that's probably a better question for the biosignature lecture. Does the variability of M-type stars on short time scales, like intense flaring, affect the atmosphere and long-term climate of planets around them? Does it play a role in the habitability of such planets? Yes, absolutely. I did not talk about solar flares in this talk, mainly because there wasn't enough time. That is indeed an important factor, and not just for M stars. So the larger stars may have higher UV fluxes. Maybe that's also harmful to life. But then some M stars are very active. Flares may strip the whole planet of their atmospheres. So this is also an area of active work, and there's certainly papers you can find that talk about that, and observations will help with that too. If we can try to look at some of these M dwarf atmospheres, if we find that very few M dwarf planets have atmospheres, that would be evidence that maybe they lose them to flares. How does the atmosphere look like on planets with a much smaller rotation time? Do they have processes like Hadley cells like we have on Earth? How does the atmosphere circulate on planets like that? What are the implications of such different types of circulations? Yeah, that's a great question. If you have a planet like Earth that's rapidly rotating rather than in the synchronous rotation. So like Earth, you're rotating, parts of the planet are always getting, there's a day-night cycle. There's papers that have been published looking at what if you slow down Earth, or what if you spin up Earth faster. So if you there's actually a great planet you can find. I think it's the range and unity of planetary circulations. I think it's from 1980 or something. And in that paper, the author takes Earth and increases the rotation rate. And you get Hadley cells, but what you do is you get more of them. If you make the Earth spin even faster, then rather than 3 where you have the Hadley cell, the ferrule cell, the polar cell, you get 5 cells like that. If you spin it faster, if you spin it really fast, you get 7. So changing the rotation rate does change the pattern of the general circulation. And in fact, Jupiter is kind of like that. Jupiter is much bigger, but Jupiter has a structure that looks like it has more than just 3 of these circulation cells. And so in a sense, the kind of circulation Jupiter has is analogous to the circulation Earth would have if it was much, much faster. Now, for the planets around low mass stars that might be in synchronous rotation, the rotation rate really depends on the orbital distance. So if this is just Kepler's law, so if you're in a fixed rotation, if you're at a fixed orbit with a fixed rotation rate, well, if you're at a fixed orbit, then the rotation rate is going to be fixed if you're synchronously rotating. And so you can't really just pick an arbitrary rotation rate if you know the orbital distance. That's going to be determined from Kepler's laws. So if you're really close into the star, you have a faster rotation rate. You get something that looks a little bit more like the Hadley cells on Earth, even for the synchronously rotating planets. If you move further out, you get more like an eyeball planet where you've got a very hot spot under the substellar point and a cold, maybe icy spot on the night side. And then you don't have as much of what looks like a Hadley circulation, but more like a giant Walker circulation where you've got, cells going from the day side of the planet to the night side of the planet. Is the presence of a sufficiently thick atmosphere alone enough for energy transfer from the day side to the night side of a tidal locked planet? Or is the presence of liquid oceans also necessary? So great question. It used to be thought that, so actually neither of those is necessary. You can have a thinner atmosphere like Earth and even take away the oceans. And the energy transport by atmospheric dynamics alone is enough to keep the night side from freezing over. So you can have a dry planet with a relatively thin atmosphere that still stays stable. But that said, yes, if you have a thick atmosphere, that would also help. And then oceans can also help. They have a large heat capacity. But yeah, these tidally locked planets seem to be robust in terms of preventing atmospheric collapse, and even in one that's very icy, you may have the substellar point still warm and having some habitable region. So yeah, they seem to be very resilient. How is habitability of M dwarf affected by their host star formation, since those planets form a much shorter timescale? Yeah, that's a great question. A little bit beyond my expertise, but I know there are some papers that look at the water abundance on planets forming in such systems. And
Jacob, maybe
go ahead. Yeah, if you have an answer for that one.
Oh, you can do that. So I think you can talk about the pre-main sequence luminosity, if that's could help in here. For the M dwarf, where they have a high luminosity before formation, before coming onto the main sequence. The Logran
well, yeah, that's right. But how does that affect habitability? It really depends on water delivery after that period. So right. If a planet could lose its water during formation, does that make all the M dwarf planets uninhabitable, or is there enough other sources of water and other volatiles to be delivered to the planets through impacts? There are some papers that have looked at this, but
Sean Raymond's paper is one of the 2007, Raymond 2007.
Raymond, I think Feng Tian has a paper on this.
Actually, 2015, Tian and Ida.
That's probably a good one to look at, is Feng Tian's paper.
Yeah. Okay.
But I think that's still kind of an open question too, whether or not all or most of these M dwarf systems will have water or will not. And observations will help, check those models too. What is the most important consideration in the habitable zone of a planetary system? Well, the way that we're defining the habitable zone is based on the carbonate silicate cycle. So in terms of that definition, I think that's the most important consideration, is does the planet have this regulation mechanism? Is there a thermostat, a way for the planet to adjust its greenhouse gas inventory based on the temperature? So that really is what defines the habitable zone concept. To study habitability, is it wiser to be concerned about the galactic environment first rather than planetary? That's a good question. There is this idea of the galactic habitable zone. There's a paper by Charles Linweaver you can look at. The galactic habitable zone tends to be about, which parts of the galaxy are most likely to have planets, and then which parts of the galaxy are most likely to be, safe enough away from high energy supernova environments, like might be closer to the center of the galaxy. So I think that's a fine enough concept. The reality is this planets we're going to be searching for in the coming decades and that we'll be able to characterize are going to be relatively close to us in the galaxy. And those are all within, this galactic habitable zone. So it's certainly worth thinking about the galactic environment. But I think in a pragmatic sense, the planets we're going to be finding are going to be nearby and going to be in pretty much the same type of galactic environment that we're in. But you should look at the Galactic Habitable Zone paper. It's definitely a fun one. And there's a few of them now that have been published. Does the habitable zone move? Yes, I think I talked about this. So that's the continuously habitable zone. And I'll share the slides and you can look up some of the papers. Because I recognize if you haven't thought about this as much as I have, it's not always immediately obvious. But the stars brighten with time over their main sequence lifetime, and so that brightening causes the ring of the habitable zone to move outward with time. And one more question. Well, that's a fun one. Is it possible to make Mars habitable again? Good question. In theory, yes. This is called terraforming. There's a big literature on terraforming. So if you're interested, you can go to Google Scholar, go to the library and look for terraforming. So yeah, the idea is that Mars today is within this habitable zone. So if you could, use our technology to kind of help Mars get to the point where it's got a habitable atmosphere, would it be able to retain that? There's ideas like you could put atmospheric pollutants like chlorofluorocarbons, which were banned on Earth, but they're very potent greenhouse gases. So you put them in on Mars on purpose to induce a strong greenhouse effect, and then maybe you could warm up the planet like that. You could think about doing something longer term where you bring cyanobacteria to Mars, and then you let those organisms take hold and start to oxygenate the atmosphere, and then you bring some algae and other plants, and you slowly start to change the Martian landscape that way. That's a really, really long time scale. So yeah, what's the time scale for terraforming? Very, very long. The first one I said, putting gases in the atmosphere, that would be shorter. You could maybe think about doing that on a time scale of hundreds of years. Introducing plants and algae that thousands to tens of thousands or hundreds of thousands of years, maybe tens of thousands for sure. Very long-term projects. I think it's fun to think about these things. Should we really do them? I don't think we're ready yet. We should figure out how to manage our own planet before we start managing other planets. But in a theoretical sense, you can think about this. And then if we're thinking about looking at exoplanets, sure, maybe we find evidence of another planet that has been terraformed. It's certainly something that we could consider. Potential biases of sampling at only nearby habitable planets for galactic habitability. Yeah, that's a good question. And okay, I'll add one thing to that. So the Kepler field, the Kepler planets are very far away, and so we do have planets that are nearby that are being discovered by the TESS mission and others. But the Kepler field is far away, and so right, if we're concerned about differences in galactic habitability, you could try to compare some from what we know about the Kepler fields to what we know about nearby planets. But that's for detection. And if we're talking about characterization of planetary spectra, it's always going to be easier to look at the nearby planets. So does that mean those are the ones most likely to have life? No, this is the story about the man who has lost his keys. and he's searching under the street light, and you go ask, what are you doing? I'm looking for my keys. Where did you lose them? Oh, about a mile away. Like, why are you looking here? Like, well, this is where the light is. So in some sense, you have that problem in astronomy that you can look in the places where you can look, but those places are not always going to be the best places to look, but those are the places we can look. So it's certainly worth keeping in mind that the planets where we can look are the planets we can look. We're going to be able to search for planets around M dwarf stars a lot easier than planets around G dwarf stars in the near future. That doesn't mean that M dwarfs are the best places for life. It means it's the best place we can look with the technology we have. So yeah, those biases are important to keep in mind for sure. And we're getting close to the time, but yeah, this is a good question. Could Earth have been terraformed? Yeah, great question. I can't say no. The question I would ask back to think about it is, what would you look for? If there were something like that, if Earth had been terraformed, what kind of evidence would there be? Could you look in the rock record for such evidence? There's a paper that's really fun by Adam Frank and Gavin Schmidt called the Silurian Hypothesis. And so it's related to this question. The Silurian hypothesis asks, what if there was other prior indigenous civilizations on Earth before human civilization? Would we have any way of being able to tell from geologic evidence? And so, yeah, there's really no reason I couldn't say Earth has not been terraformed, other than so far the geologic evidence we have has not found anything anomalous that requires us to invoke terraforming as a hypothesis. And so really you just have to ask yourself, what would you look for to convince yourself that had occurred?
Those are the questions we have, right?
I think that's it for the chat.
Yeah. Thank you so much. It was very interesting session, and also a lot of questions, and you patiently answering all of them. It was a huge list of questions today. So thank you so much for a wonderful session. Dr. Ravi, would you like to say something?
I just want to thank Jacob for the fantastic talk, and thank everyone and Prachi as well for attending this. So Jacob, if you are okay, could you share your slides with Prachi when you can?
Oh yeah, I'll email you the slides. They're Google Slides, so I'll just send you the link. Yep.
Okay.
And this is just one note for the participants that we will be sharing the recordings with you today. You will get it via an email. So you have to log in, you have to log into your Gmail or to your Drive with the same email ID that you have registered through. So we have given access, the view only access to only those email IDs with which you are registered for the course. So that we will be sharing today, and we will keep on adding to this folders as and when the lectures happen. So just a note of that. Okay, thank you so much, everyone. Thanks for joining.
All right, thank you. See you, everybody.
See you. Bye.